Hello guys, we continue our series about using ML algorithm for betting. Today we will use a method which is called random forest. We'll use it to predict the results of football games. And the idea is that we build several models, and by averaging the forecast we get the final prediction. That's it. So let's take a look how it works. Let's suppose we have a game between Leicester and Wolverhampton, and we want to calculate the probability of home team winning. So today we will learn how to build several models, and by averaging the forecast we get the final prediction. So here we have 4 models. The first for decision tree. So first one gives us a prediction which is equal to 70, second one 60, third one 50, and the last one also 60. So we take the average, we got 60. That's our final prediction. First of all, we must generate the features that influence the final result. To calculate the probability of home team winning, I have highlighted 4 features. The first one is the percentage of games where home team scores more than 1 goal when plays at home. That's important. So we don't take all games for home team, only when it plays at home. The second feature is the percentage of the games where home team concedes more than 1 goal, again when plays at home. And the third and fourth are the same, but calculated for away team when it plays away. In fact, we could add more features. For example, how many games home team has won when plays at home, how many games away team has lost. But for our purpose, for understanding how the model works, 4 features is enough. From these features, we could build our data sets. So here I have a list of games. That's English Premier League. So for each game, we have feature values for last 10 games. That's why the numbers are so round. And we have a column, the result. So the result is 1 when home team wins, otherwise 0. So here I have only 10 games, but for real calculation I took last 5 or 6 seasons. You will see it further. What's next? Next we begin to build our model. The idea is to find a feature that best separates our data set, and by best I mean that our data set will be separated in such a way that one part contain the mostly games where home team wins, and the other part will contain mostly the games in which home team lost. In general, we need to identify which feature has the greatest impact on the final result. So, how to do this? We take every feature and sort our data set by ascending order of value. For example, table 1 is sorted by the home team scoring. And that's why at the top of the table we have the teams like Burnley, Newcastle, teams that rarely score, and then the bottom of the table we have this team like Liverpool, Arsenal. So then we look at the distribution of the home team wins and see that this feature, home team scoring, doesn't separate our data set very well, because both the teams that rarely score and the teams that score a lot win about the same. Then we take the next feature, how home team concedes the goal, and again we see that this feature doesn't work well because the home team wins are evenly distributed. But when we take the feature 3, how away team scores, we see you can see the border here. So we see that if away team really scores, sorry, the home team wins 4 times out of 5, and vice versa. When away team scores more than 25%, the home team wins only 1 time out of 5. So we take this feature to split our data set, and you can see that I have already highlighted this table by yellow sign. And finally we should check the 4th feature, and we see that the 3rd one is better because the 4th doesn't separate very well. Home team wins are also evenly distributed, so we choose the feature 3. As a result, we have the simplest model, our first decision tree, with only one condition. The condition is when away team scores less than 25%, the probability of home team winning is 80%, based on our data set, of course, 4 times out of 5. And conversely, when away team scores more than 25%, the probability of home team winning is only 20%. That's it. And here I want to emphasize one important point. There were only 10 games in our toy data set, but in reality we have many times more games. To build a real model, we need at least 500 games. If we have 500 games, we can divide our big data set into 2 parts, not necessarily equal. One part can have, for example, 260 games, and another part 240. And then these parts can be divided by the same way, so that our data set will have 3 levels of depth. To demonstrate this idea, I have taken 20 games. In the first step, we divide our data set by variable x3, because as we can see, when away team scores less than 25%, home team mostly won 5 times out of 7. Yeah, and that will be our first leaf in our decision tree, and another leaf when the away team scores more than 25%. I've put this remaining part into separate table, and we try to divide this table the same way. So we take each variable and try to identify which feature splits better our data set. In this case, it's x1. As you can see, the threshold is 45%. When home team scores less than 45%, so the probability of home team winning is only 2 times out of 7. And when home team scores more than 45%, so the probability of home team winning is much higher. Okay, so what is important? If we didn't split this remaining part, we can conclude that the games where the home team is down, like Burnley, Newcastle, and the home team is top team like Liverpool, Chelsea, these games are the same in terms of probability of home team winning, which is obviously wrong. So we apply our algorithm to this part, to this leaf, and end up with a more accurate model with 3 levels of depth. Okay, let's go back to our model. So we have one decision tree with only one condition, but in reality to have the only one decision tree is not enough to have a good, accurate prediction. Why? Because the only one decision tree is unstable and can change its prediction sometimes even dramatically. To demonstrate these ideas, I add to our dataset 2 games. If we look to our previous models, so the condition was if away team scores more than 25% of the time, so probability to win for home team is only 20%. But after adding these 2 games, if we recalculate the outcome in this leaf, we see that if away team scores more than 25% of the time, so home team wins 3 times out of 7. It's 43 instead 20%. So we see that prediction changes dramatically. Okay, we see that one decision tree is not enough, so we should take somewhere the second one, the third one, and so on. Where? We can get the old games, we can take the old games, we can go deep into archive, but we will have a problem because these old games are not up to date. So what is the solution? The solution is to generate from our initial data set a new one. How? I will show you on next slide. Okay, so now we come to the question what the random forest is. The first step is that we need to generate new data sets. To do this, we use a method which is called Bootstrap, and the idea is that we have our original data set and we take the random element from this data set and put into new data set, and as if we were returning this element back, so we can select it one more time. And I show you an example on the slide. We have the original data set, which consists of 4 colored balls: blue, yellow, green, and red. You can imagine that these balls are games. And we have generated 4 data sets. As you can see, the first one consists of 3 yellow balls. So yellow ball was chosen 3 times. Blue ball was chosen 1 time, and green and red were not chosen once. The same way, the same situation with the second data set. So we took red ball 2 times, yellow and blue 1 time, and green wasn't chosen once, and so on. Okay, we have 4 new data sets, so we can calculate the prediction. How did we calculate the prediction? So we take each feature and try to find which best separates our data set. And now we come to the second step. So the first one was to generate new data set, and the second one to calculate prediction, but we have 4 features, but we don't take all features. We take the random, that's why the forest is called random. We take random subsample of these features. So in my case, in my example, I exclude only one random feature, and what is the reason to do it? The reason is to have our predictions more independent and less correlated from tree to tree, because all these data sets, they are different, but they were generated from one original data set. So if we use all features for these data sets, we will have the similar prediction. But if we exclude some features, we will have the wide range of predictions. That's our goal. We don't want to have a similar prediction. Our goal is opposite, to have a wide range of prediction. It's like taking the best and the worst scenario and get the prediction by averaging them. By the way, I have here only 4 features. If you have a lot of features, you can choose only half of them. That's okay. And using these 2 methods, bootstrap and excluding features, we will have the more, as practice shows, we will have the more accurate predictions. What this looks like in practice. We have our original data set, this white table with 10 games sorted by the best variable x3. So what we do, we have to generate the new data set from this one, from original. How we do it, we take the random game from white table, put it into the second table, and as if we were returning this game back, so we can select it again. And finally, what we have, we see that, for example, Liverpool, Watford have been taken 2 times, Arsenal, Brighton 2 times, Burnley, Man City 2 times, Southampton, Chelsea 1 time, and some games like Norwich, Burnley has not been selected once. Okay, so we've got a new data set, and as I said before, we exclude one random feature. In this table it's x4, and we try to define which variable best separates our table between only these 3 features. And we see that the best separator for our data set is variable x2 when it's how often home team concedes goal, and we see when the home team concedes goal rarely, less than 15%, so probability to win 3 times out of 3, 100%. And opposite, if the home team concedes goal more than 15%, so the probability of home team winning is only 1 of 6. Okay, so the same method to generate the table 3. That's interesting that the game Burnley Man City have been selected 3 times, and again a lot of games are not in at the table at all. So here we exclude x3, and we see that the best variable is x4, how Waiting concedes the goals when plays away, and the threshold is 15%, so when away team concedes goals rarely, like Chelsea and Man City, the probability of home team winning is only 20%, and that makes sense. And the same situation with table 4. Again, we generate new data set. Aston Villa Tottenham has been taken 3 times. Again, some of games are not on the table, and we exclude x1, and we see that the best variable to separate our data set is x2, but if you compare the table 2 and table 4, you see that the threshold is different. So here the threshold is 45%, and when away team, home team, sorry, concedes the goal when playing at home, a lot of times, like Aston Villa, like Watford, so probability of home team winning is 0. That's it. We have finally 4 models, 4 decision trees. Thus, if we need to calculate the forecast for our upcoming game, for example, Tottenham versus Leicester, we get the prediction from each decision tree, and by averaging them, we've got a final prediction. Here I have drawn the conditions for our 4 models, and we substitute our game features to each decision tree. So for the first decision tree, we have probability of home team winning is 20%, since the condition is x3 more than 25%, and we have a 30. For secondary threshold, for x2 is 15%, so we have 30. That's why we go to the right hand leaf, and our probability to win is only 14%. The second tree separate our data set by variable x4, and the threshold is 15, so we have the value of 60. That's why we again go to the right leaf, and probability to win for this decision tree is 80%. Note how big difference is. And the last decision tree gives us the probability 15%, since x2 less than 45%. Yeah, that's correct. And by averaging all this yellow value, we got the final prediction is 41%. Is probability of home team winning for this game. So I hope the idea is clear. Let's move on to coding. Let's see what happens here. In this cell I download all needful libraries. Here I download all the games from English Premier League for last 8 seasons. So you see that it starts from 2014 and 3036 games in this data set. So here I have the big function that calculate how often team scores or concedes more than 1 goal. What else here? I split my data set into train and test. Train data set consists the game up to 2021, and the test data set is the games consists the games of the last season. You can check it. So data frame before games up to 2021. That's correct. In this cell we have a function that calculates our prediction using the algorithm of random forest, and there are 3 important points I would like to note. The first one is number of estimators. It is the number of decision trees. In presentation we used only 4 decision tree. Here we come closer to reality and use 30. Usually 30 is enough. The second important parameter is the minimum samples in the leaf, because we cannot divide our data set until there are 1 or 2 games left in the leaf. So usually we adjust our algorithm so the minimum samples of leaf should be 5 or 10% of the length of the whole data set. And the third important parameter is the maximum of features to use in each decision tree. So we have 4, as we see in the presentation, and as I said, we exclude in this case only one random feature. We don't know which one. and for each decision tree we use only 3 features. That's correct. So, and here we add 3 columns to our data set. The first one, ref prediction, is the forecast calculated by all 30 decision tree by averaging day forecasts. It's our normal prediction. Let's call it normal, okay. The second column and the third column, which I added, is called decision tree 1 and decision tree 2. Here we have the predictions used by only one decision tree. So we take one decision tree, calculate the prediction, put in the column decision tree 1, then we take another decision tree, calculate its prediction and put in the last column, which is called decision tree 2. In this case, I take a slice of my data set to show you how the results differ. So if we take, for example, the game between Southampton and Arsenal, we see that the final prediction is 40.9, but the decision tree 1 gives us 38.5, and decision tree 2 gives us 36.8, and both results are wrong. And if we restart the calculation, we see that the final prediction of the game between Southampton and Arsenal pretty similar to the previous calculation, 39.6, and again decision tree 1 and decision tree 2 both are wrong. So we get the middle ground by averaging all of them. So that is the point of that is the point to use this algorithm. So it always gives us the middle ground. So that's all. Thank you for your attention. See you on the next video.